Alright, in this video we're going to start Chapter 7, which is Applications of Integration. Integration has a wide variety of applications. For each application presented in this chapter, you begin with a known formula, such as the area of a rectangular region, the volume of a circular disk, or the work done by a constant force. Then you learn how the limit of a sum gives rise to new formulas that involve integration. And the biggies here, we're going to get through at least these first three sections. Section 7.1 is how to use the definite integral to find the area of a region bounded by two curves. That's in Section 7.1. And then we'll get to 7.2 and 7.3. That's how to find the volume of a solid, a three-dimensional solid, of revolution by the disk method and the shell method. And if we have time closer to the end of the year, we might get into 7.4, how to find the length of a curve and the surface area of a surface of revolution. And what do we have here? This is what I'm talking about, a solid, a 3D solid. And when we get to that 7.3, that is the disk method. You know how we chopped the area of a region under a curve into rectangles and then made the rectangles thinner and thinner so there were infinitely many of them. We'll do the same thing with three-dimensional shapes. Here we see a bunch of round disks stuck together. If we chop it into more and more disks, we'll see it turns into an oval when we have infinitely many disks. So here in 7.1, we're going to check out the area of a region bounded by two curves. We're going to find that region using integration. We will find the area of a region between two intersecting curves by integration, and describe integration as an accumulation process. Let's think about this here. We have two curves, a downward opening parabola F, and then we have an upward opening, looks like parabola G. What is the region between the two curves? What is its area? Well, we can find the area under a curve. You know, we could find this area from A to B of the function f of x. And we can also find the region under curve G from A to B. So the big idea here is we are going to find this region between the curves by taking the definite integral from A to B of the upper function. You know, the function here that is up on top is f of x. And we're going to subtract the function that is under g of x. We're going to integrate that and, you know, take our upper and lower limits and run it through our antiderivative. And we'll find the area of the region between those curves. So with a few modifications, you can extend the application of definite integrals from the area of a region under a curve to the area of a region between curves. So we consider these functions f and g that are continuous on our interval from a to b. If, as in figure 7-1 on the previous slide, the graphs of both f and g lie above the x-axis and the graph of g lies below the graph of f, you can geometrically interpret the area of a region between the graphs as the area of the region under the graph of g subtracted from the area of the region under the graph of f. So here's the area we want to find. We take the area under f, which is this integral, and we subtract the area of the region under g, this integral. And we get the area of the region between the curves, the integral from a to b of the upper curve minus the lower curve. And here, if you want to read this on your own, it goes more into the limiting process. We go back into some of that summation notation. And the big idea here is we're taking the area between the curves and chopping them up into rectangles using our summation notation. And then we will let the width of each rectangle approach 0, make them infinitely thin, like we did when we were finding the area under a curve. So here in the blue box is the big idea, area of a region between two curves. F and g are continuous functions on the interval from a to b. G of x is always under f of x for all values of x in our interval. Then the area of the region bounded by the graphs of f and g and all vertical line and the vertical lines x is a and x is b is, and here's our definite integral. So we're going from x is a to b, that's our lower limit a to upper limit b. And then we have our upper function f of x minus our lower function g of x. And we are integrating with respect to the x variable. So let's try one out. Take it for a test drive. Example 1. Find the area of the region between two curves. Find the area of the region bounded by the graphs of y equals x squared plus 2. That's a parabola opening up, y-intercept 2. And y equals negative x, or y equals negative x plus 0. So we have a y-intercept of 0 and a slope of negative 1. Going downhill, here's our line, g equals negative x. And above is our upward opening parabolic curve, x squared plus 2. We want to find the area of the region between them from x is 0 to x is 1. So from x is 0 is this line, to x is 1 is this line. We want to find the area of this region. We could almost do it without calculus, but we do have this curve is sort of messing it up. We have this straight line at the end. It would almost be a trapezoid, and we could just use a simple geometry formula. But the curve messes it up, so we are going to have to apply some calculus. And let's make this official. I'll even go right by the formula. We were going from a to b of the function f of x minus g of x integrated with respect to x, delta x, or dx. So from this problem, our definite integral is going to be from 0 to 1. X is 0 to x is 1. We need our upper function. What function is always higher than the other? Well, here we can see it's the parabola, and that is the x squared plus 2 function. So we're going to have our f of x function is x squared plus 2, and then we're going to minus the other function, the lower function. And for that, it was g of x was negative x. And we are integrating with respect to x. So working within the brackets, let's combine anything we can. We have x squared plus 2 minus a negative x, so we add the opposite, and that becomes a positive x, all integrated with respect to x, dx. And I like to write mine in proper order of our exponents. So our x squared term will be first, plus x is next, plus 2. And again, we are integrating with respect to x. So I think we're ready to take the antiderivative. And this is a nice easy polynomial function. So our first term, x squared, we raise the power by 1, x to the third, divided by the new power or multiplied by the reciprocal. 1/3 x to the third. Plus, this is x to the first power, raise the power by 1, x squared, divide by the new power or multiply by the reciprocal. Plus, this is 2. You could think about it as 2x to the 0. So that becomes 2x to the first power divided by the new power 1, which we will not write down. And we are evaluating this definite integral from 0 to 1. So we're ready to plug in our upper limit. The 1 goes in for x. And this is nice because 1 to the third is 1, 1 squared is 1, x to the first will be 1. So we're going to have 1/3, and this x to the third is 1 to the third, or 1, plus 1/2 times, well, 1 squared is 1, plus 2 times 1 is 2. And then we would subtract our lower limit evaluated through the integral, and this is nice because every term has an x. So this will be 1/3, 0 to the third is 0. 1/2 of 0 squared is 0. Plus 2 times 0 is 0. So all of this becomes a minus 0, and we don't need it at all. So let's work with our fractions. 1/3 times 1 is 1/3, plus 1/2 times 1 is 1/2, plus 2. So if we get common denominators here, our common denominator would be 6. So 1/3 written as 6 would be 2/6, plus 1/2 written as 6 would be 3/6, plus 2 would be 12/6. And let's see if we add those up, we get 17/6. And they did not give us any kind of unit on this, but remember we are finding an area between a couple curves. So let's just remember that would be some kind of units squared. 17/6 units squared. Now we could also have an area of a region between intersecting curves. In example 1, the graphs of x squared plus 2 and g of x was negative x do not intersect at all. And the values of a and b are given to you explicitly. A more common problem involves the area of a region between bounded by two intersecting graphs, where the values of a and b must be calculated. That's the biggie. So we want to find the region lying between two intersecting graphs. And let me get the picture out of the way because that might make this a little too easy right off the bat. We want to find the area of the region bounded by these two functions. F of x equals 2 minus x squared, and we know a negative x squared is a downward opening parabola, and g of x equals x is a line of slope 1. So we might have a line looking like this, and we know that there's going to be 2 points where these graphs are going to intersect, and we want to find the area of the region between them. So the first point is to find these values. And how do we do that? Well, we set the functions equal to each other. So we're going to set f of x equal to g of x to find intersecting points. To find points of intersection. So f of x is 2 minus x squared. We're going to set that equal to g of x was equal to x. And I'm going to get everything on one side and set it equal to 0. So the x squared hops over and becomes a positive x squared. We already have a positive x there. This 2 jumps over and becomes a minus 2. And this is all equal to 0. So how do we solve this? We factor. What are the factors of x squared? Has to be x and x. What are the factors of 2? 2 and 1. Where will the signs go to get the middle term to be a positive 1? So it'll be a positive 2 and a negative 1. If we add 2 and negative 1, we get positive 1 in the middle. If we multiply them together, their product is negative 2. So now we set each of these factors equal to 0. X minus 1 equals 0 means x is 1. And x plus 2 equals 0 means x is negative 2. So there are the x values where our graphs are going to intersect. And points of intersection. And you know there's going to be 2 points, and we found the x values. Negative 2 is one of the x values, and 1 is the other x value. So let's see, what are the y values? I don't know if we need them, but let's just find them anyway. So here we have g of x equals x or y equals x. So that's easy enough. You know, if this is our x value, negative 2, by the g of x function, our other value would be negative 2. This x value was a 1, so y equals x for the g of x function, so this is going to be 1, 1. There are the points where our graphs intersect, and the important ones are the x values. Those will be the lower and upper limits of our definite integral. We also got to know which function is above the other function across this interval. Is the line above the parabola, or is the parabola above the line? One way we could do this, we know f of x is 2 minus x squared. And g of x is equal to x. What points lie between negative 2 and 1? Well, 0. What happens if I plug a 0 in? F of 0 here would be 2 minus 0 squared, or 2. That's how high this function is at 0. And here we would have g of 0 is equal to 0. So it looks like this is the upper function. F of x is always above g of x. F of x is always greater than g of x. So we want to make sure f of x is our upper function. So we have a definite integral, and we know that goes from negative 2 to 1 of f of x is our upper function, 2 minus x squared. And we are going to minus g of x, the lower function, which in this case is just plain old x. And we're going to integrate that with respect to x. So let's see here, distribute the negative sign, and we can write our polynomial in order. So that's going to be negative x squared minus x plus 2 integrated with respect to x. So this will be a nice easy integration. Raise the power by 1, divide by the new power. So here we have this is going to become a negative x to the third divided by 3 minus x squared divided by 2, and then plus 2x, and we will evaluate from negative 2 to 1.
The bad thing about this problem is our lower limit is not 0, so we're actually going to have to evaluate both and then combine a bunch of fractions. So I'll use red for the upper limit. That 1 is going to drop in for all the x's. And this won't be too bad. So here we're going to have a negative 1/3 minus, this becomes 1/2. And then we're going to add 2 times 1 is 2. And then we subtract our lower limit, which is negative 2. So here we're going to have negative 2 to the third, which is negative 8, and this is going to make that into a positive 8. Plug the negative 2 in for this x. Negative 2 squared is positive 4. 4 divided by 2 is 2. So minus 2. And then plug the negative 2 in here. 2 times negative 2 is going to be minus 4. And if you compute all this, get your common denominator, combine everything up, and you will get a 9x. And then let's check out the graph that goes with this. So here's what it looks like. We do have our downward opening parabolic curve, our slope of line of slope 1 going through the origin. And the first thing we did when we set the functions equal, we found that they intersected at x is 1 and at x is 2. And we did find the y values that went with those x values. We really didn't need it, but hey, all math is good math. And then we had to figure out, okay, which of those functions was above the other one at all times. Well, we plugged in a nice easy value, x is 0, and we found that the parabolic curve had a 0 value at 2, and the line had a 0 value at 0. So that told us that the parabola was always above the line, the missing 0. And then we did our integration, f of x minus g of x, and we integrated from x is negative 2 to x is positive 1.
All right, let's see what's going on here in example 3. Example 3, a region lying between two intersecting graphs. The sine and cosine waves intersect infinitely many times, bounding regions of equal area as shown in figure 7.7. So here's our sine wave, and our cosine wave is in the lighter gray. They intersect infinitely many times, and they create these regions. And these regions are actually going to have the exact same area. We want to find the area of one of those regions. So let's see here. How are we going to start this out? First, we got to find out a good intersection point. Where does sine x equal cos of x? Well, let's divide both sides by cosine. Sine divided by cosine is the same thing as tangent of x equals cosine divided by itself is 1. Where does tangent equal 1? Let's see here. If we look at our unit circle, we're going to have tangent of x equal to 1. That happens at 1/4 pi, and again at 5/4 pi. So this gives us our interval that we will be integrating across. This is sort of our A value, our lower limit, our B value, our upper limit. Now across this interval, if we look at the picture, sine and cosine are always switching places. You know, for a while sine's above cosine, and then they flip-flop. Across this interval, which one is on top? If the graph is handy, or your graphing calculator is, you could, do a quick graph of each and figure out, okay, from here at a quarter pi all the way to 5/4 pi, the sine wave is on top. Or what you could do is pick an interval somewhere in there, and this might be an easier way to think about it. Here is a 1/2 pi. What is greater, the sine of a 1/2 pi or the cosine of a 1/2 pi? Well, the sine of a 1/2 pi is equal to 1. The cosine of a 1/2 pi is 0. So across this interval, our sine wave is the one on top. Across this interval, sine of x is greater than cos of x. And that's going to help us set up our integral. So remember, our integral is from a to b, or in this problem, that's going to be pi over 4 to 5 pi over 4. And then we want to subtract our functions. And again, in this example, sine of x is greater than cos of x, so it's going to be sine x minus cos of x integrated with respect to x. And let's figure this out. Oops. So let's take the antiderivatives. What is the antiderivative of sine x? Well, that's a negative cos. Minus, what is the antiderivative of cosine? Well, that's sine. And we are evaluating from quarter pi to 5/4 pi. So let's see here. We got to evaluate those limits. So first I'll do red. We're going to plug in the 5/4 pi. Negative cos of 5/4 pi minus the sine of 5/4 pi. And after we find that quantity, we're going to subtract the evaluation of the lower limit. Negative cos of 1/4 pi minus the sine of 1/4 pi. And then we go to our handy unit circle. And what is the cosine of 5/4 pi? Well, that is negative root 2 over 2. And this negative out front is going to make that positive, root 2 over 2. Minus the sine of 5/4 pi is also negative root 2 over 2. And we're minusing that, so it becomes a plus root 2 over 2. And that became a plus because it was minus the negative. So that's going to be our first quantity. And let's see here. We got this negative. We could do this right now. I didn't do this last year, but we could distribute this negative. So we're going to add the cosine of 1/4 pi. Cosine of 1/4 pi, that's first quadrant. Everything's positive, root 2 over 2. And then we're going to add the sine of 1/4 pi. That is also a root 2 over 2. So let's see here. If we look at all four of these, we have a common denominator of 2. And we have a root 2 plus another root 2 plus a third root 2 plus a fourth root 2. So we have 4 root 2's collected on top. And then we see here we could reduce this. 4 divided by 2 is 2 square roots of 2. That is our final answer. That is the area of the region between the sine and the cosine graphs' points of intersection.